Hi again, everybody, and welcome to your final example of Chapter 5. This has been our chapter on Newton's laws and forces, and we discussed a variety of forces, and including tension and friction and contact forces and spring forces and connected objects. And this is our final connected objects problem. We've done an Atwood machine, which is really another name for a machine with connected objects, with 2 masses, with 3 masses, and now with 4. So my assumption here is that you're going to be familiar with how to do this. I'm going to go through it somewhat quickly, not belabor too many of the points, and we'll get through this. What we're going to do is we're going to solve for the acceleration of the masses of the whole system. Oops, I didn't mean to do that. Acceleration of the masses of the whole system, and the tension in the, once again, I'm going to change this to cables. So the tensions with an S. Tensions in the cables. In fact, let me color them so that we can, well, you know what, I'm not even going to color code them too much. I'm just going to call this, well, let's actually name the boxes. I'm going to call this box 1, 2, 3, and 4, okay? And so I'm going to call this tension 1, 2. I'm going to call this tension going up over the top 2, 3, and this tension 3, 4 right there. Okay? Remember, tension works both ways. It works both directions, so it's the tension pulling between each of these individual objects right here. All right, again, as a full screen, I'm going to solve for the acceleration of the system. And then I'm going to solve for tension 1, 2, tension 2, 3, and tension 3, 4. So the net force on the system equals the mass of the system times the acceleration of the system. All right, but the net force on the system is also the sum of all those forces. Of all the forces that are acting. So the net force on the system is going to be, all right, let's take a look at these right here. On the right-hand side, we've got 12 plus 5 kilograms, and that's going to be 17. So on this side, it's 10 plus 2. That's only going to be 12. So there's going to be more mass, therefore more weight force on the right-hand side, so it's going to be moving clockwise. Even if we get this wrong, it doesn't matter, but I think if we kind of look ahead and see that that's going to be going clockwise, it makes sense to make that direction positive and counterclockwise negative. Okay? So what forces are acting in the clockwise positive direction? Well, that's going to be, actually we'll do these in color. M4G, right? Mass 4 times gravity. What else is going to be in the clockwise direction? Well, that's going to be plus M3G, right? This is this one right here, M3 times gravity. What's going to be acting in the negative direction? Let me do this one in orange, not yellow, because yellow won't show up very well. This is acting in the negative direction, right? The mass of 2 times gravity. So minus M2G, and I'm going to have to do the other one below it because I ran out of space. Mass 1 times gravity minus mass 1 times gravity. Also acting in the negative direction, okay? So let's set all these equal to mass of the system times acceleration of the system. By the way, when I rewrite it, I'm going to factor out the G. G. I'm going to put that out front and then just have mass 4 plus mass 3 minus mass 2 minus mass 1. So that way you'll see kind of what I'm doing with that. I'm going to write it all in black for now. So setting these two statements equal to each other, we can say the mass of the system times the acceleration of the system equals G, putting it out front, times mass 4 plus mass 3 minus mass 2 minus mass 1. So therefore, the acceleration of our system is going to be G out front, I should say, gravity times M4 plus M3 minus M2 minus mass 1, all over the sum of those forces, right? Because we're taking our mass of the system and dividing it down below. So it's going to be mass 4 plus mass 3 plus mass 2 plus mass 1. So the difference in the forces is still going to have to accelerate the whole mass of the system. Okay, so that's going to be divided by M4 plus M3 plus M2 plus M1. All right, so 9.81 times the quantity, mass 4, that is 5 kilograms, plus mass 3, that's 12 kilograms, minus mass 2, it's minus 10, minus mass 1, that's minus 2. All right, all divided by 5 plus 12 plus 10 plus 2. Well, I almost ran out of space right here. So the acceleration of the whole system is going to be what? Well, let's go ahead and key that in. And I get a grand total of 1.69 meters per second squared. Well, that's really squeezed in down there. Sorry about that. We'll write it over here on the far left-hand side. Our acceleration of our system equals 1.69 meters per second squared. Okay? So we got our acceleration of the system by taking the mass of the system times the acceleration of the system and setting it equal to all the forces that are acting in that system, either in the positive direction or in the negative direction. All right? So we've got our mass of the system, which, by the way, is going to be the mass of each one of those independent boxes. Let's take all this now and shrink it down, and then solve for each of the individual tensions, all right? I'm going to put this up here and give myself a little bit more space. I wrote that acceleration of the system pretty big because we're going to need to refer back to it. But let's solve for the tension between 1 and 2, all right? For tension 1, 2, all right? Let's look at which one of those boxes, box 1 or box 2, would be easier to deal with. Probably box 1, right? Because it only has that one thing connected to it. So let's draw box 1. Box 1 is right here. So what forces are acting on box 1? We've got M1G, right? And the other force acting on box 1 is tension 1, 2. That's why we picked box 1, right? Because tension 1, 2 is acting on box 1. All right, so we can say the net force on box 1 equals tension between box 1 and box 2 is acting in the positive direction, right? It's pulling upwards on box 1. M1G, the weight force, M1G is acting in the negative direction. It's acting counterclockwise, and we call that the negative direction, all right? The other statement we can make about box 1, the net force on box 1 equals the mass of 1 times the acceleration of box 1, which we know to be the acceleration of the system, right? Let's just go ahead and set them equal to each other and solve for tension between 1 and 2. You know what? I'm going to move this up a little bit. Tension 1, 2 minus mass 1 times gravity equals mass 1 times acceleration 1. So therefore, tension between 1 and 2 is going to be M1 acceleration 1 divided by, or sorry, not divided by, sorry, I'm not dividing, I'm adding, right? We're going to add this to the other side. Mass 1 times acceleration plus M1 times gravity. We can factor out that M1 to make it a little bit easier. So acceleration of 1 plus G. Let's find out what that is. So what's the mass of 1, mass of box 1? That's 2 kilograms, right? 2 kilograms times the sum of A1 plus gravity. And again, acceleration of 1 is the acceleration of the whole system because they're all accelerating at the same rate. So that's going to be 1.69 plus 9.81. That's going to give us our tension between 1 and 2. So 1.69 plus 9.81 times 2, we get 23 newtons. That's tension between box 1 and box 2. All right, let's find between 2 and 3. 4 T23. Okay, so we can look at box 2 or box 3. Since we already know, look at box 2 for a second. Since we already know the tension between 1 and 2, we can call that one of the forces. on box 2. We don't know tension between 2 and 3. And we also don't know the tension between 3 and 4 right here. So 3 might be a little bit harder to determine. But let's use box 2 as our example because we know all the forces now that are acting on box 2. It's like we're working our way around. We're going this tension and then this tension and then this tension right here. Okay? So let's look at box 2, which I will write in orange. Right there. Okay? So box 2. First of all, the downward tension is mass, I'm sorry, not mass 1, mass 2, right? We're on box 2. Mass 2 times gravity. But there's also another downward tension as well. And that is the tension between box 1 and box 2, which we just solved for. T1 and 2. This guy right here. There's tension pulling down on box 2, as well as the weight of box 2 pulling down. What's pulling upwards? What's pulling upwards is what we're solving for. That's tension between box 2 and box 3. All right, so we can say that the net force on box 2 equals mass of box 2 times the acceleration of box 2, which is the acceleration of the system. We can also say that it's the sum of all those forces. So again, what's the positive direction? Up, or clockwise, you'd say, is a positive direction. So this is going to be positive. These two guys are going to be negative, so we have to write them like that. So tension between 2 and 3 minus mass 2 times gravity minus tension between 1 and 2. Let's set them all equal to each other. Mass of 2 times the acceleration of 2 equals tension 2, 3 minus mass 2 gravity minus tension between 1 and 2. All right, I didn't leave a whole lot of space down below that right there, so I'm going to need to move upwards. What are we solving for again? We're solving for tension between 2 and 3, right? Between these guys right here. So I'm going to add mass 2 gravity over and add tension between 1 and 2 over as well. So we're going to get something like this. Tension between 2 and 3 equals mass of 2 times the acceleration of 2, or the system, right? Plus mass 2 gravity, because that's being added over, plus tension between 1 and 2. Okay? That's all we need. So all we need to do is just plug in what we know. Mass 2 times acceleration of 2. So that's, what is mass 2? It's 10, right? 10 times, what's the acceleration of 2? You can see it's the acceleration of the system, right? That's 1.69. 1.69 meters per second squared. I think we're all thankful that we're not putting in units right here, although it's not a bad idea. Plus mass 2 times gravity. All right, so that's 10 times 9.81. There should be a point in there. There we go. Plus the tension between 1 and 2. And we know what that is. That's 23 newtons, which is what we solved for in the first part. Okay, so the tension between 2 and 3 is going to be that as we do all that math right there. Okay, and I get a grand total of 138 newtons. Very different tension between boxes 2 and 3 than between 1 and 2, right? But again, it's because we've got different forces acting between the boxes. And just like a long time ago we did the contact forces between the boxes, the tension forces are going to be different as well. All right, lastly, let's solve for box for tension 3, 4. All right. Now, for the last one, we used box 2 to find the tension between 2 and 3 because we knew the tension between 2 and 1 and the weight force and all that stuff. For this last one right here, we have the luxury, once again, of picking which box we want to use. And in my opinion, box 4 might be a little bit easier to use because it only has one tension applied to it. That's the tension between box 3 and 4, which is what we're solving for right there. So let's use the blue box. You could use the green one if you wanted to, but I think it'll be a little bit more complex. The blue box, to me, has less forces acting on it, so less to add up. So that's m4 times gravity, right? Mass 4 times gravity, so it's a weird looking 4. And what's the force that's acting upwards? That upwards force is tension between 3 and 4. We'll write that in black. All right, T 3, 4. So the net force on box 4 equals mass of 4 times the acceleration of 4, which is the acceleration of the system. Net force on box 4 is also these two forces acting against each other. Which is acting in a positive direction? Which one? This one is, right? Because clockwise is positive, so this M4G is actually acting in a positive direction. M4G, that's positive. So tension between 3 and 4, which acts on both boxes, but we can use either one to solve for it, is going to be, as far as box 4 is concerned, it's going to be in the negative direction. Oops, I put a plus sign. I don't want to do that. It's minus. Minus T3, 4. Let's set these equal to each other. T3, 4. Oh, no, I messed it up already. Mass. By the way, there is a very, I'm going to draw a very faint line right here to separate these. Sorry about that. Students do that sometimes too to separate out problems, and I can understand why, because you can't always predict where stuff's going to go. Mass 4 times acceleration 4, acceleration of the system, is going to be equal to M4 gravity minus tension between 3 and 4. Let's just have that tension and mass 4A force switch sides. So tension is going to be positive. T3, 4 equals M4 times gravity. And remember, this gets subtracted over to that side because we want tension all by itself. Minus mass 4 times acceleration of 4. All right. I'm not going to worry about factoring out the M to make it easier, because even though it might be easier, it's going to take up more space, and we want to finish this problem up. So let's just say M4. What is that? That is 5 kilograms, right? 5 times G, 9.81 meters per second squared, minus the quantity 5 again, times the acceleration of the system. What's the acceleration of, well, acceleration of 4, which is the acceleration of the system, which is 1.69 meters per second. 1.69 meters per second. And that's going to give us our tension between 3 and 4. The tension in the rope between 3 and 4. So 5 times, I get 40.6. 40.6 newtons. And that's our final answer. So we can see that the tension between all these strings, tension in here, and the tension in here, is all going to be different. It varies quite a bit. I think it's understandable that the tension in the middle, right here, is going to be the most because you got heavy weights pulling on either side of it. But the tension in these little strings, these little ropes right here, is definitely going to be different because it depends on what the masses are in between all those. So that was quite a hefty problem. Thank you for hanging in there with me to the end. It's still shorter than some problems we've done, but it must just mean that we're getting better and more efficient at doing these. So thanks again for staying with me, and if you have any questions, make sure you come see me, and I'll see you on the next one.